team of researchers looked at light from a planet 124 light years away, ran it through one of the most sensitive instruments ever built, and found a chemical signature that, here on Earth, is produced by exactly one thing: living organisms in the ocean. Or at least, that's how the story was first told. The team who found it called it the strongest evidence yet that life might exist somewhere beyond our solar system. And then, over the following year, a wave of other scientists went back through the exact same data and came to a very different conclusion. Stick around, because I'm going to walk you through exactly what was found on exoplanet K2 to the 18b, why the original claim generated so much excitement, and why so much of the scientific community now says the evidence doesn't actually hold up the way it first appeared to. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now. Because there's a lot more coming out of the search for life beyond our solar system. To understand why this particular claim generated so much attention, you first need to understand what K2-18b actually is, and why astronomers picked it out of the thousands of known exoplanets to study this closely in the first place. K2-18b orbits a small, cool star called a red dwarf, sitting about 124 light-years from Earth in the constellation Leo. The planet itself is considerably larger than Earth, roughly 8.5 times more massive and about 2.5 times wider, placing it in a category of planet called a sub-Neptune, something bigger than any rocky world in our own solar system, but smaller than gas giants like Neptune or Uranus. What made K2-18b interesting from the start is its orbit. It sits inside what astronomers call the habitable zone, the specific range of distance from a star where temperatures could plausibly allow liquid water to exist on a planet's surface rather than freezing solid or boiling away entirely. A team of researchers led by Niku Madhusudan at the University of Cambridge proposed a specific theoretical model for what a planet like K2-18b might actually look like beneath its atmosphere, something they named a Hycean world, a term combining the words hydrogen and ocean. Under this model, K2-18b would have a deep global ocean of liquid water, covered by a thick, hydrogen-rich atmosphere, an environment genuinely different from anything in our own solar system, but one that, according to the researchers proposing it, could theoretically support microbial life, similar in some ways to the kind of simple marine organisms found in Earth's own oceans. The Hycean concept itself represented a genuinely useful expansion of how astronomers think about potentially habitable worlds, not just a convenient label attached after the fact. Before this framework was proposed, most searches for habitable exoplanets focused specifically on rocky, Earth-sized worlds orbiting at the right distance from their star. Since Earth remained the only confirmed example of a habitable planet, astronomers had to work from. The Hycean model, first formally described by Madhusudan and colleagues in 2021, argued that a much broader category of planets, considerably larger than Earth and covered in oceans far deeper than anything on our own world, might also support life under the right conditions, so long as the thick hydrogen atmosphere above that ocean didn't create surface temperatures and pressures too extreme for biology to survive. That broader definition matters practically too, because sub-Neptune planets like K2-18b are actually far more common throughout the galaxy than Earth-sized rocky worlds, and considerably easier to study with current telescope technology, given their larger size and thicker atmospheres, which produce a stronger, more detectable signal when starlight passes through them. Using the James Webb Space Telescope, the same team first detected methane and carbon dioxide in K2-18b's atmosphere back in 2023, molecules consistent with, though not exclusive to, this Hycean ocean scenario. But it was a second look at the data that generated the real headlines. Alongside the methane and carbon dioxide, the team reported a faint, low-confidence signal that appeared consistent with a molecule called dimethyl sulfide, usually abbreviated DMS. On Earth, DMS is significant for a very specific reason. It's produced almost exclusively by marine phytoplankton, tiny ocean-dwelling organisms that release the gas as part of their normal biological activity. And for decades, atmospheric scientists have flagged DMS as one of the most promising biosignature gases to search for on other planets, precisely because no significant natural, non-biological source for it had ever been confirmed here on Earth. If you're finding this as fascinating as I did while researching it, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. In April of 2025, Madhusudan's team published a follow-up analysis using a different instrument aboard Webb, this time reporting spectral features, consistent with either DMS or a closely related molecule called dimethyl disulfide, detected at a statistical confidence level of about 3 sigma, and at concentrations dramatically higher, potentially tens of parts per million, than anything found in Earth's own atmosphere. Madhusudan himself, speaking publicly about the results, described them using words that ended up in headlines around the world, calling the findings the strongest evidence yet that life may exist on a planet outside our solar system, while also stating clearly that the team was remaining cautious and that this did not represent a confirmed detection of life. That distinction between strongest evidence yet and confirmed detection matters enormously, and it's exactly the distinction that got lost as the story spread. A 3 sigma statistical confidence level, while worth taking seriously in scientific terms, is considerably short of what researchers typically consider a fully secure discovery. In particle physics, for comparison, researchers generally require a 5 sigma confidence level, corresponding to roughly a 1 in 3.5 million chance of the result being a random fluke, before they're willing to call something a confirmed discovery at all. A 3 sigma result, by contrast, still carries a meaningfully higher chance of turning out to be a statistical artifact, especially when the underlying data is as faint and noisy as light collected from a planet more than 100 light years away. To put that in more concrete terms, a 3 sigma result still carries roughly a 1 in a few hundred chance of being nothing more than random statistical noise, dressed up to look like a real signal. That might sound like reasonably good odds in an everyday context, but for a claim as extraordinary as detecting a potential sign of life on another planet, a result that still has a meaningful chance of simply being a fluke isn't considered sufficient grounds for anything close to a confirmed discovery within the scientific community. It's a genuinely useful piece of evidence worth investigating further, but treating it as settled fact skips over exactly the kind of verification process that separates a promising early result from an actual scientific consensus. That gap between initial excitement and final confirmation is exactly where this story has spent the better part of the following year, and it's worth walking through what actually happened next, because it's a genuinely useful window into how real science works when a claim this big gets put under a microscope. Almost immediately after the April 2025 announcement, other research teams began independently reanalyzing the exact same raw data Madhusudan's team had used, applying different statistical methods and different assumptions to see whether the DMS signal held up. A team led by researcher Jake Taylor found that the specific statistical approach used in the original analysis appeared to inflate the apparent significance of the detection, and that once a more conservative method was applied, the evidence for DMS became considerably weaker. A separate team, led by researcher Raphael Luque, conducted what's called a joint analysis, combining data from all 3 of Webb's relevant instruments together rather than analyzing each one separately, and concluded that there simply wasn't statistically significant evidence for either DMS or dimethyl disulfide once the complete picture was considered. Researcher Luis Wellbanks and colleagues took a slightly different approach, using what's called an agnostic retrieval method that doesn't assume ahead of time which specific molecules should be present in the atmosphere, and found that the existing data was consistent with a range of other, entirely non-biological molecules, just as well as it was consistent with DMS. Then in July of 2025, a NASA-led team uploaded its own independent reanalysis, and their conclusion added yet another layer of caution to the story. Their study confirmed that K2-18b really does appear to have a genuinely complex, water-rich atmosphere, supporting at least part of the original excitement around this planet. But on the specific question of dimethyl sulfide, they found no conclusive evidence for it at all, joining the growing list of independent teams unable to confirm the original signal at any statistically robust level. There's a second, entirely separate problem that emerged alongside all of this statistical back and forth, and it strikes right at the core assumption that made DMS exciting as a biosignature in the first place. Throughout this entire debate, scientists had been operating on the understanding that DMS had no known natural source anywhere in the universe other than biological activity, which is precisely what made its potential detection so significant. In 2024, a separate research team examining data collected from a comet found DMS present in genuinely abiotic, non-biological cometary material, demonstrating for the first time that this specific molecule can form through purely chemical processes with no life involved at all. That finding didn't just weaken the K2-18b claim specifically. It undermined the broader theoretical foundation that DMS was considered an unambiguous, exclusively biological signature in the first place, a foundation multiple published papers throughout 2023 and 2024 had explicitly relied upon. It's worth pausing to explain why any of this matters beyond the specific fate of one exoplanet's reputation, because this entire episode is actually a pretty valuable window into how legitimate scientific claims about extraterrestrial life are supposed to be evaluated. The famous astronomer Carl Sagan is widely associated with the phrase that extraordinary claims require extraordinary evidence, And few claims are more extraordinary than detecting signs of life on a planet we'll likely never visit directly. That standard means a genuinely responsible claim of this magnitude has to survive exactly the kind of process K2-18b has been going through. Independent teams reanalyzing the same raw data using different methods, researchers actively searching for alternative explanations, and results that only get treated as solid once they've survived that kind of sustained adversarial scrutiny rather than simply being accepted at face value because the original finding sounded exciting. Judged against that standard, the evidence for life on K2-18b currently falls considerably short, not because the original researchers did anything improper, but because the broader scientific community did exactly what it's supposed to do when a claim this significant gets published. None of this means the story is necessarily over. And it's worth being fair to what the original researchers actually got right, since a lot of that groundwork remains scientifically valuable, regardless of how the DMS question ultimately resolves. K2-18b's atmosphere really does appear to be genuinely unusual and worth continued study with confirmed detections of both methane and carbon dioxide that multiple independent teams agree on. The broader Hycean world concept, a class of ocean-covered hydrogen atmosphere planets that might exist in meaningful numbers across the galaxy, remains a legitimate and actively studied area of exoplanet science, even among researchers who remain skeptical of this specific DMS claim. And Madhusudan's team has continued pushing for more observation time, arguing that additional data collected over more transits of the planet in front of its star could eventually push the statistical confidence of any real signal, whether DMS or something else entirely, up to a level that would satisfy even the most cautious skeptics. There's also a deeper, more physical question hanging over this entire debate that researchers still haven't fully resolved, regardless of what happens with the DMS signal specifically. Some scientists studying K2-18b have raised doubts about whether the Hycean Ocean scenario is even physically plausible in the first place. Separate entirely from any biosignature question, modeling work published by researchers including Nicole Wogan and Oliver Shortall has suggested that the specific combination of methane and carbon dioxide detected in K2-18b's atmosphere might actually be more consistent with a hot, high-pressure environment, unsuitable for liquid water or life, rather than the cooler, ocean-covered world the original Hycean interpretation proposed. If that alternative picture turns out to be correct, the entire premise of a habitable ocean on K2-18b would need to be reconsidered, regardless of what molecules do or don't turn out to be present in its atmosphere. That disagreement over the planet's basic physical structure runs even deeper than most casual coverage of this story tends to acknowledge. Some researchers have proposed that K2-18b might not have any ocean at all, Hycean or otherwise, and could instead be better explained as a mini-Neptune with a deep, largely gaseous interior and no clearly defined solid or liquid surface anywhere beneath its atmosphere. Others have suggested the planet could even be predominantly molten, with surface conditions far too hostile for liquid water to persist in any stable form. Resolving that more fundamental question, what K2-18b actually looks like beneath its outer atmosphere, will likely require additional observations specifically designed to probe deeper into the planet's structure, independent of whatever conclusion researchers eventually reach about dimethyl sulfide. It's also worth understanding just how difficult this kind of measurement actually is from a pure engineering standpoint, because it helps explain why disagreements like this one are almost inevitable with current technology. Webb isn't photographing K2-18b directly. Astronomers are instead measuring tiny, extraordinarily subtle changes in starlight as the planet passes in front of its host star, changes small enough that different molecules in the planet's atmosphere absorb specific, narrow slivers of that light in ways that overlap and blend together in genuinely ambiguous ways. Untangling which specific molecule produced which specific dip in the light requires enormously sophisticated statistical modeling, and different teams making slightly different assumptions in that modeling process can reasonably arrive at meaningfully different conclusions from the exact same underlying dataset. That's not a flaw unique to this particular study. It's simply the reality of trying to determine detailed atmospheric chemistry on a planet that's over 700 trillion miles away, using nothing but the faint, filtered light that happens to pass through its atmosphere on its way toward Earth. This particular technique, called transmission spectroscopy, has become one of the most powerful tools in modern exoplanet science. But it comes with real, inherent limitations that no amount of additional analysis can fully eliminate on its own. Every transit of K2-18b in front of its star lasts only a few hours, and astronomers typically need to combine data from several separate transits just to build up enough signal to say anything meaningful about the planet's atmospheric composition at all. Background noise from the star itself, subtle variations in the telescope's own instruments, and the simple faintness of the signal. being measured all compound together, which is part of why a claim resting on a handful of observed transits can look statistically solid to one research team's modeling approach and considerably weaker under a different team's assumptions, even when both teams are working from identical raw data and acting in complete good faith. So what does all of this actually add up to? A real, published, peer-reviewed detection of an interesting signal in the atmosphere of a genuinely unusual exoplanet, described honestly by its own discoverers as tantalizing but unconfirmed, that has since been extensively challenged by independent researchers using the same raw data, and further complicated by the discovery that the specific molecule in question isn't actually the unambiguous biological fingerprint scientists once believed it to be. There's a broader pattern worth recognizing here too, one that extends well beyond this single planet. K218b isn't the first time a potential biosignature has generated enormous public excitement before ultimately requiring years of careful follow-up scrutiny. Similar cycles have played out before with claimed detections of phosphine in the atmosphere of Venus, a molecule initially proposed as a possible sign of microbial life in that planet's clouds back in 2020, only for multiple follow-up studies to significantly weaken the original claim, and with earlier, ultimately unconfirmed claims of fossilized microbial structures in meteorites, believed to have originated from Mars. In each of these cases, the same basic pattern repeats. An initial finding generates justified scientific interest and often disproportionate media attention, and then the slower, less headline-friendly work of independent verification either strengthens or substantially weakens the original claim over the following months and years. K218b, at this point, sits squarely in that same ongoing process, and where it ultimately lands remains a genuinely open question. That's not the same story as scientists confirming alien life, and it's worth being honest about that gap, because the real story here, a fascinating exoplanet, a genuinely provocative but statistically fragile signal, and an entire scientific community working in real time to figure out whether it holds up, is honestly just as interesting as the more dramatic version that ended up in so many headlines. If stories like this one, grounded in real published research and honest about where the evidence is genuinely uncertain, are what you want more of, subscribe to this channel and turn on notifications, because K218b is almost certainly going to get observed again, and there's a real chance the next round of data finally settles which side of this debate turns out to be right. Thanks for watching, and I'll see you in the next one.